Hello everyone, this is tutorial 2 for PC-TAS, the phase change thermoacoustic simulator. Today we're going to discuss building a system and guesses and targets. Our system for today will be a standing wave refrigerator. You see it, the picture right here. This is a loudspeaker driven refrigerator. It is the first phase change thermoacoustic refrigerator, and it was designed by Yang et al. You can read more about it here in this paper here, about its performance, its design, and so on. Now the components for this refrigerator are those. You see a loudspeaker right here. This is what generates the sound and drives the refrigerator. Then you have a resonator here, a long piece of duct. Afterwards, you have two heat exchangers, a cold heat exchanger and an ambient heat exchanger, and between them you have a stack. And essentially the interaction of the stack with the sound wave drives heat from the cold heat exchanger to the ambient heat exchanger. Finally, we have a short duct here at the end of the system, a short duct and a wall. So we're going to build the system in PC-TAS. We're going to build it excluding the loudspeaker, even though you can simulate loudspeakers in PC-TAS, but we're going to start from here, from this point right here, and build the rest of the system. So let's start. I'm going to open PC-TAS, and I'm going to start with the system properties. I'm going to call the system Young refrigerator, and capitalize the R just because. So this is the system. The mean pressure, we're going to leave it as it is, atmospheric pressure. That was how the system operated. The frequency, the working frequency was 86 Hertz. So we're going to work with 86. And dry switch is off because this is a phase change refrigerator, so it's not dry. And the working mixture is fine. Inert is air, the reactive is water, all this is fine. Now, as for the initial conditions, the mean temperature was 280. This was known. This is the cold temperature, the temperature at the beginning. And as far as pressure and velocity go, we don't really know them, so we're going to give them pretty random values right now. 500, 500, and 0.01. And that's all the system properties. Now we're going to go ahead and build the system. We're going to start with the resonator. We'll call it duct 1. Give it a length of 0.745. Diameter, this is the diameter of the entire system, 0.047. We're going to go for OK. Then afterwards comes a plate heat exchanger. We're going to put it right here. We're going to call it CHX, stands for cold heat exchanger. Give it a length of 0.02, diameter usual 0.047, and this is half the plate spacing. This is 9e minus 4, corresponds with a plate spacing of about 2 millimeters. Porosity was 0.6, and the heat input is not really known. We're going to go with 0.5 for now. And this is the cold heat exchanger. Afterwards comes the stack. This was a rectangular stack, so we're going to put it here. We're going to call it stack. Give it a length 0.095, diameter 0.047, and these are the height and width of the pores, the rectangular pores. We're going to give both of them a value of 4.6 e minus 4 here and here. And finally, we have the porosity of 0.85. That's fine with us. After the stack comes another heat exchanger. Sorry, that was a stack. This is a heat exchanger. We're going to call it AHX, ambient heat exchanger. Length of 0.02. Diameter as usual. Plate spacing in this case was 2.5 e minus 4. Corresponds to half a millimeter plate spacing. Porosity of 0.67. And heat input of -1, the ambient heat exchanger. And the last component, an ambient duct. We're going to call it duct 2. Give it a length of 0.055, diameter of 0.047. So this is the system. This is a geometry. This is the original refrigerator. We're going to go ahead and run it and see what the results are. One thing before running the system, I want to show you some additional properties. Some of the properties cannot be decided upon creation of the component, and you need to change it afterwards. So first of all, we have the jackets. Ducts and cones and compliances, all of them have jackets. The jacket essentially determines whether the component is insulated or else it is in good contact with the environment. If it is insulated, the jacket should be off. If it is in good contact with the environment, the jacket should be on. In our case, the cold duct was insulated, so the jacket will leave it off, but the ambient duct was open to the environment, so we're going to put the jacket on. You can also determine the solid material of many of the components, specifically the heat exchanger were both for copper, so that's fine, and the stack was a ceramic stack, so that's also fine. But we could change it potentially to a stainless steel stack or a tungsten stack, etc., etc. So these are the components, and now we're going to run the system. And the system was run, and we're going to look at the results, and we're going to see quite a bit of problems with the results. First of all, the pressure. The pressure at the end of the system is around 2000 pascals, and the actual measured pressure amplitude was around 4000. So that's problem number one. Second of all, the velocity. The velocity at the end, at the wall, should be 0 because it is a wall. But here we did not specify it to be 0 in any way, so it is not 0, and that's problem number 2. Third problem is the total power. We see here a jump in the total power from the ambient heat exchanger to the second duct. This is because of the jacket. The jacket induces a jump in the total power, and this is another problem. Last of all, we have the solid temperature. The calculated solid temperature of the ambient heat exchanger is 283 K. The actual solid temperature was around 295 K. So this is the last problem. And we need to fix these problems, and we're going to do it by adding guesses and targets to the system. So the guesses are essentially values that we so far didn't really know when we simply guessed them. Targets are values that we do know, but they are not determined by us. They're calculated, so we need to target them. So we'll start with the guesses. We said that the oscillating pressure and velocity at the beginning were pretty much random, so we're going to make all of them guesses. The real part of the pressure, we're going to make a guess. The imaginary part of the pressure, we're going to make a guess. And the real part of the velocity. So these are 3 guesses right here. And next, we're also going to add as guesses the heat inputs in both heat exchangers, because neither of them were known. So we're going to add guess here, heat, and add guess here. That's 5 guesses. And now for the targets. So we wanted to target a 0 velocity at the end. We actually have a designated target especially for that. It's called a hard end, and you put it when you have a wall in your system. I'm going to call it end. And it has a specific target which you can target, the target value. This is essentially the inverse of the acoustic impedance at this point. And if you target the inverse of the acoustic impedance to be 0, you essentially target the velocity to be 0. You could also target the velocity as well to be 0, but there might be some convergence issues. So this is the recommended way to do this. We also want to target the pressure at the end. I'm going to target the absolute value. I'm going to give it a target value of 4,300. Notice that when you create a guess or a target, then you can change the values through here, through the table. The automatic value is usually the current value of the property. So in our case, all these guesses have the current values that we specified as a guess. And here for the target, we wanted to change it to 4,300, so we changed it to here. This is the target. We also want to target the solid temperature of the ambient heat exchanger. So we're going to add a target here, solid temperature. And we said it was 295. And finally, we want to solve the jump, the jump in the total power that we want to fix. So we have a special target just for that. We call it the jacket target. We put it right here, right after the ambient heat exchanger. We call it JT, jacket target. And we're going to target the target value. The target value here is essentially targets the difference between the acoustic and total power. And if we target it to be 0, we're solving the issue of the jump in total power. So these are all the properties we specified. These are all the guesses and targets we specified. And now we're going to go ahead and run the system with guesses and targets. Now I'm going to give you a spoiler to say we're going to get lucky. Our values for the guesses here are good enough for us to converge. In reality, you need to have some estimate of the guessed values that is pretty close to the actual value. Otherwise, you will not converge. So here, of course, we came prepared. We came prepared with good values, but that's not always the case. In this case, we run the system, and the algorithm converge, and we can now look at the graphs, and we can see the pressure is around 4,000 as we specified. The velocity is 0 at the wall, which is good. The total power no longer has any jumps. And if we look at the solid temperature, it is now 295, the MBT exchanger. So all of that is just fine. So that was all for today. We talked about guesses and targets. We understood how to add guesses and targets and how to run the system with guesses and targets. And we'll discuss the remaining issues in the third and last tutorial. So goodbye everyone, have a nice day.